This chapter is considered as the most important chapter in the book that covers the fundamentals of the analysis of algorithm efficiency and a gateway to other chapters. Basically, in this chapter, you will learn in details how to analyze and find the efficiency of both recursive and non-recursive algorithms. And in order to do that, we will outline a general framework that will be used for analyzing the efficiency of algorithms. Previously, we have already mentioned that there were two kinds of efficiency: time efficiency and space efficiency. Although the general framework can be used to measure both of these efficiencies, we will be focusing on how to use this framework to measure only time efficiency. To start analyzing an algorithm for a certain problem, you need to know the meaning of an instance of this problem and also the meaning of its input size. Let us start with an example of an algorithm that solves a problem to give you a brief introduction on how to find an instance of this problem and how to find its input size. By considering the search problem, which is the problem to search for a key in an array, we would like to give a brief introduction on how to find an instance of the problem, how to determine the problem input size, and how to find and express the time efficiency of the problem as a function of the input size. We will view the search algorithm as a function that has input parameters and a return value. So the algorithm will be represented by a box, and the algorithm has two input parameters. The first parameter is an array of size n, and the second parameter is the key element that we want to search for in the array. The name of the algorithm is search, and it returns an integer. If the search key is found in the array, the algorithm will return the position or the index of the key in the array. And if the key or the search key is not found in the array, then the algorithm will return -1, indicating that the key is not found in the array. So the array and the key are the input parameters to the algorithm. So these are the input parameters to the array. Now suppose you would like to test the algorithm to get some results. Then you need to provide sample of input parameters to the algorithm. Let us have some examples. For the first example, suppose we want to test the algorithm for an array that has the elements 3, -1, 7, and 2. So the size of this array is 4. And suppose we want to look for the key that is equal to 7. As another example, suppose we have the array that its elements consist of 6, -2, 0, 8, and 9. So the size of this array is 5. And suppose that we would like to search for the key that is equal to 10. For the first example, the search is successful because the key element is in the array, but for the second example, the search is not successful because the key is not found in the array. In fact, these examples are called instances of the problem. So they represent input parameters to the algorithm, and they represent instances of the problem. So if you want to talk about the problem, then these are instances of the problem. And when you talk about the algorithm of the problem, then these will be samples of input parameters to the algorithm. It is given as a fact that if the problem input size is increased, then the running time for the algorithm is also increased. So the problem input size is defined as a numerical parameter that influences or affects the running time of the algorithm. Now, how to find the problem input size for the search problem? We need to look for a numerical parameter. so that if this numerical parameter is increased, then the search algorithm will take long time to search for the key in the array. Notice that if the size of the array is increased, then the running time for searching for the key will also increase. So therefore, searching for a key in the algorithm takes longer time on large size of arrays compared to the running time for searching for a key on a smaller size of arrays. So we can consider the size of the array as the problem input size. Why? Because it affects and influences the running time of the algorithm. If it is increased, the running time is also increased. So therefore, we write here that for the search problem, the problem input size is equal to n, which is the size of the array. The time efficiency or complexity of an algorithm measures the running time of this algorithm. And as you know, the running time depends or relies on the problem input size. In this case, we can express the time efficiency as a mathematical function of the problem size. So here is the function for the time efficiency, that the input parameter is the problem input size. And for our problem, which is the search problem, the problem input size is n. So n will be the input parameter to the time efficiency. Suppose the label of the function is t. So we represent the time efficiency as a mathematical function in terms of n. So we write the time efficiency as t of n. For the search problem, the time complexity is equal to n. Later we will show you how did we find this answer when we analyze the search algorithm. As a final remark, in this problem, notice that the algorithm input parameters are not the same as the time efficiency input parameter. The input to the algorithm is an instance of the problem, and the input to the time efficiency is the problem input size. For some problems, the problem input size is the same as the input parameter to the algorithm. We will see later some examples on such type of problems when we study how to find precisely the time efficiency of algorithms. In the analysis of algorithms, we can view algorithms as we demonstrated in the previous example as functions in the mathematical sense, matching between inputs within a domain and output within a range. An input to a function might be a single value or a collection of information. The values making up an input are called the input parameters of the function. For algorithms with inputs, the obvious observation that almost all algorithms run longer on larger inputs. For example, algorithms take longer time to sort large arrays or multiply large matrices. To find the efficiency of an algorithm, you need to find first the problem input size, then do the analysis and express the time efficiency as a function of this input size. The problem input size is defined as a numerical parameter that affects and influences the running time of the algorithm. I mean, if the value of this parameter is increased, then the running time of the algorithm is also proportionally increased. The problem size can be specified according to the problem type. I mean, whether the problem is sorting, searching, string matching, graph algorithm, etc. At the end, the algorithm efficiency is expressed as a function of the problem input size, because it's a parameter that relatively affects the running time of the algorithm. For an algorithm where the input is an array or a list, the problem size is typically measured by the length or number of elements of this list. If the length of the list is equal to n, then the size of the problem is also equal to n. For algorithms evaluating a polynomial of degree n, you know that if we have a polynomial of degree n, then the number of its coefficients is equal to n plus 1. Therefore, the size will be either the polynomial's degree, which is equal to n, or the number of its coefficients which is larger by 1 than its degree. Now for an algorithm computing the product of two n by n matrices, the input size might be n if the two matrices are square, or the total number of elements or entries in the matrices being multiplied, denoted by capital letter N. Now for a graph algorithm, the problem size consists of two variables. The first one represents the number of vertices, and the other one represents the number of edges. Finally, for an algorithm where the input is a single number, the problem size may be measured by the number itself or the amount of bits required to represent the number in binary, depending on context of the problem. In this case, if n is the number, then the number of bits in n is determined by the floor of log n base 2 plus 1. Previously, we've mentioned that the problems or algorithms were like mathematical functions with input parameters. A specific selection of values for the parameters of the algorithm solving the problem is called an instance of a problem. For example, the input parameter to a sorting function might be an array of integers of size n. So any particular array of integers with a given size and specific values for each position in the array would be an instance of the sorting problem. And here is an example of an array of size 7 with elements 8, -2, 5, 4, 3, 8 and 0 considered as an instance of the problem. Considered as an instance of the sorting problem. Similarly for a searching algorithm, if the input parameters are an array of integers of size n and a searching key, then any particular array of integers of size n with specific values and a key would be an instance of the searching algorithm. And here is an example of an array of size 7 with a key equal to 9. This is an instance of the sorting. For the GCD algorithm, the input parameters are the two positive integers m and n, and any particular values for these two positive integers would be an instance of the GCD algorithm. And here is an example of one of the instances of this problem. M is equal to 342 and n is equal to 212. Finally, for the shortest path problem, the input parameter might be a two-dimensional array that represents the adjacency matrix for a graph of size v, for a graph of size v by v, where v is the number of vertices of the graph. Any particular adjacency matrix with a given number of vertices and specific values for the entries of the matrix would be an instance of the shortest path or problem. And here is an example of an instance of the shortest path problem that is a two-dimensional array representing the adjacency matrix for the graph with some values of the element representing the graph. Now as a remark, different instances of a problem might generate the same output. However, no particular instances generate different outputs. And as another remark, most interesting problems include an infinite collection of instances. Now, to show that an algorithm is correct, it must work correctly on every instance of the problem. And to show that an algorithm is incorrect, give only one instance that makes the algorithm incorrect.